Every video about artery health gives you a list. Olive oil, pomegranate, leafy greens. And honestly, the list isn't wrong. But here's what nobody tells you. It's incomplete. And that gap, that missing piece nobody's talking about, may be the exact reason why people who do everything right still end up in the cardiologist's office with a calcium score that keeps climbing. Not because they weren't trying, because they were only activating one of the four biological mechanisms your body actually needs to protect your arteries. Today, we fix that. If you've been following this series, you already have a head start. You know what's quietly building inside your arterial wall. You know why your standard blood tests aren't catching it. You've been asking the right questions. What you haven't had yet, until right now, is the complete answer. Here's what the research actually shows. Slowing, stabilizing, and in some cases beginning to reverse the markers of arterial plaque buildup isn't one process. It requires four separate biological mechanisms, each one needing a different compound, each one failing to compensate when the others are missing. Think of it like a lock with four tumblers. Turn 1, 2, even 3, and the door stays shut. All four have to move together. The Predimed trial tested this in the real world. 7,447 participants, 5 full years, and the group following standard low-fat dietary advice, the advice most people in this audience have been given at some point, had the worst cardiovascular outcomes of the three groups. Not second worst, worst. Not because they were eating badly, because they were activating one mechanism while unknowingly shutting down two others. They had the best intentions and an incomplete map. In this video, I'm going to give you the complete map. 4 mechanisms, 4 compounds, 1 meal with the specific doses the studies actually used. Not a list, a protocol. These 4 things sitting in front of me right now, arugula, a halved pomegranate, a bottle of olive oil, and a K2 supplement, don't look like much, but each one of them is a separate biological intervention targeting a different step in the same disease process. By the end of this video, you'll understand exactly why that distinction changes everything about how you think about what you eat. But before we get to the protocol, I need to take you somewhere most people have never been, inside the wall of your artery. Because what's actually happening in there is not what most people think. And until you understand the mechanism, until you can see it, the protocol is just another list. I'm not your doctor, and honestly, that's precisely why I can show you this. I've spent years reading the research that never made it to the waiting room, the studies that were published, peer-reviewed, and then quietly left on the shelf while the same incomplete advice kept circulating. The conversation most people are having about arterial health is happening at the wrong level. Everyone's talking about what to eat. Nobody's talking about what the food actually needs to do inside the arterial wall once it gets there. That's the gap. And that gap has been costing people decades of healthy life they didn't know they could still protect. Before we go further, drop a comment right now with just your age, nothing else. I want to see who's watching, because what I'm about to show you matters differently depending on exactly where you are in this journey. Now, before I explain the mechanisms, I want to be honest about something personal. When I started reading this literature, I had the same framework most people have. Eat well, cholesterol goes down, arteries stay clear, simple cause and effect. The reason I kept digging, kept reading study after study long past the point most people stop, is because that framework kept failing the people I was reading about, including my father. He did everything right, and I mean everything. Low-fat diet, years of it, walked every morning, 3 miles, same route, same time. Took his medication without missing a single day. His compliance was almost perfect. And yet, multiple strokes later, I found myself sitting with a stack of research papers asking the same question over and over. What was still progressing? He was reducing what was going in, Nobody had ever turned on the exits, the biological pathways that remove the damage already building inside the wall. The medication was managing the pressure, the diet was reducing the inputs, but the exits, the four mechanisms I'm going to show you today, were never activated. Not because the science didn't exist, it did, it does, because nobody translated it.
That translation is what this channel exists to do. I'm going to show you the exits, all four of them. To understand why the protocol works, you first need to understand what's actually happening inside your arterial wall. Not the simplified version, the real version. Because most people, including most people who consider themselves informed about heart health, have the wrong mental picture. And when you have the wrong picture, even the right advice doesn't fully make sense. So let me give you the right picture. Imagine a neighborhood that starts out clean, organized, well-maintained. Then one day, something goes wrong with the waste management system. Garbage starts accumulating inside the walls of the buildings, not on the streets where anyone can see it, but hidden inside the structure itself. The city keeps sending cleanup crews, but the crews get overwhelmed. They get trapped inside the walls, and when they die in there, the debris they were trying to clean up becomes part of the structure itself. That's not a metaphor I invented. That's almost exactly what's happening inside your arterial wall when plaque forms. And here's why it matters. If you think plaque is just grease building up on the inside of a pipe, like limescale in a faucet, you'll accept solutions designed for a pipe problem. But that's not what this is. This is a biological cascade happening inside living tissue, and it requires completely different thinking. Here's the actual sequence, step by step. Step 1. LDL enters the wall. Your arterial wall has an inner lining called the endothelium, a single layer of cells, incredibly thin, separating your bloodstream from the tissue underneath. LDL, the cholesterol particle most people know as bad cholesterol, can penetrate that lining and get trapped in the space just beneath it. Think of it like water seeping through a wall and getting absorbed into the material inside. Step 2. The LDL oxidizes. Once LDL is trapped inside the arterial wall, it gets exposed to a chemically reactive environment. It oxidizes, meaning it undergoes a kind of molecular damage, similar to how iron rusts when exposed to air and moisture. It changes it fundamentally. Step 3. Your immune system misidentifies it. Here's where the cascade really begins. Your immune system is constantly patrolling for threats. When it encounters normal LDL, it recognizes it as a familiar particle, not a threat. But oxidized LDL, that looks like a foreign invader, like something that doesn't belong. So your immune system does exactly what it's designed to do. It sends in the cleanup crew. Those cleanup cells are called macrophages. Their job is to engulf dangerous material and neutralize it. Under normal circumstances, they're extraordinarily effective. But this situation isn't normal. Step 4. The macrophage gets overwhelmed. The macrophage engulfs the oxidized LDL, but macrophages aren't built to process large amounts of fat. As they keep absorbing more and more lipid, tiny fat droplets start accumulating inside them. The cell becomes engorged. Under a microscope, it looks foamy, riddled with fat droplets. That's a foam cell. And here's the critical problem. A foam cell cannot escape. It cannot migrate back through the endothelium into the bloodstream. It's permanently trapped inside the arterial wall, a cleanup crew member that went in to help and can never leave. Step 5. The foam cell dies, and that's when the real damage happens. When a foam cell dies, it doesn't disappear cleanly. It ruptures, releasing everything it had accumulated inside: cholesterol crystals, inflammatory signals, cellular debris.
That material doesn't get cleared. It accumulates, layer by layer, over months and years. That accumulation is your plaque. Write this down, because this is the mental model everything else in this video builds on. Plaque is not passive buildup of cholesterol coating the inside of a pipe. It is the end result of a biological cascade. LDL enters the wall, oxidizes, gets engulfed by an immune cell. That immune cell becomes a foam cell. The foam cell dies, and the debris accumulates into plaque. That cascade, repeating silently over years and decades, is what shows up on a calcium score. Now here's the part that most people, including many patients who've had extensive cardiovascular workups, have never been told. The danger of plaque isn't primarily about narrowing. Most people imagine heart attacks like this. Plaque slowly builds up like sediment in a pipe, eventually blocking the flow completely. That mental picture feels intuitive. It's also incomplete, and the incompleteness of it has led to some significant misunderstandings about cardiovascular risk. Here's what actually happens in most heart attacks. A mature plaque doesn't just sit there quietly growing, it develops a structure. On the outside, there's a fibrous cap, a thin covering like a skin over the plaque. Underneath that cap is what's called a necrotic core, a pocket filled with dead foam cells, cholesterol crystals, and inflammatory material. When that fibrous cap ruptures, often triggered by inflammation, sometimes by a sudden physical or emotional event, the contents of that necrotic core are exposed directly to the bloodstream. The bloodstream responds immediately. A clot forms at the rupture site. If that clot grows large enough to block the artery, that's your heart attack. Here's the finding that genuinely changes how you think about this. A plaque that is blocking 40% of an artery can be significantly more dangerous than one blocking 70%. Read that again. 40% can be more dangerous than 70%. Why? Because the 40% plaque is often more inflamed, more biologically active, with a thinner fibrous cap, meaning it's far more likely to rupture. The 70% plaque, while more obstructive, may be stable and calcified, with a thick fibrous cap that holds. This is exactly why stents, the procedure that opens a blocked artery, don't significantly reduce the risk of future heart attacks in stable patients, according to studies including the Courage and Ischemia trials. In acute situations and high-risk presentations, stents remain critical and life-saving. But in stable coronary artery disease, a stent addresses the obstruction without addressing the rupture-prone plaques that cause most events. The goal isn't just to open the pipe, it's to stabilize and regress the plaques most likely to rupture. And that requires completely different tools. This is also why standard cardiovascular medicine, focused almost entirely on reducing inputs, is only half the equation. Reducing inputs matters, but it's only one side of the biology. What almost nobody is addressing are the exits, the biological pathways that remove the damage already inside the wall. Those exits exist. They're documented. They have names. And I'm going to show you exactly how to activate all 4 of them. So we've established what's happening inside the wall. The foam cell is trapped. The cleanup crew that went in to help is now part of the problem. The debris is accumulating. Now the question becomes, is there any way to reverse that? Is there a biological mechanism that can actually pull cholesterol out of the foam cell, back out of the arterial wall, and send it somewhere it can be processed and eliminated from the body? The answer is yes, and it has a name. The answer starts with a protein you've probably never heard of. Think of every foam cell in your arterial wall as a room with a lock on the door. Inside that room, accumulated cholesterol that should never have been there. Cholesterol that got trapped, oxidized, engulfed, and is now contributing to plaque that grows a little more every year. The lock on that door is a protein called ABCA1. Don't worry about what the letters stand for. What matters is the function. ABCA1 is the exit mechanism. It sits on the surface of the macrophage, the foam cell, and its job is to eject cholesterol back out of the cell, handing it off to HDL particles circulating in the bloodstream. HDL then carries that cholesterol to the liver, where it gets processed and eliminated from the body. This process has a name: reverse cholesterol transport, and it is the primary biological pathway documented to remove cholesterol directly from inside macrophages in the arterial wall, and the most well-studied route for reducing foam cell accumulation at the source. Read that again. Not slowing the accumulation, not stabilizing it, reversing it, running the cascade backwards. Now, here's where it gets important and where most standard medical conversations fall short. You've probably had your HDL measured. Your doctor looked at the number, compared it to a reference range, and told you whether it was good or low. But here's what that number doesn't tell you. The metric that actually predicts cardiovascular risk, the one that multiple large population studies have identified as an independent predictor of heart disease, isn't the amount of HDL in your blood, it's the function of your HDL. Specifically, its ability to accept cholesterol from foam cells via ABCA1. This is called cholesterol efflux capacity. Think of it this way. Imagine you're measuring how effective a fire department is by counting the number of trucks in the fleet. You might have 20 trucks.
But if the hoses are broken, the water pressure is low, and half the drivers don't know the routes, the truck count tells you almost nothing about how well fires are actually being put out. Your HDL number is the truck count. Cholesterol efflux capacity is whether the hoses work. And in most doctors' offices, including excellent ones with excellent physicians, nobody is measuring whether the hoses work. The conversation ends at the number. If you watched our video, "Your Stiff Arteries Are Starving Your Brain After 60, you'll remember Thomas. Calcium score of 836. Blood pressure perfectly controlled. His medication was working exactly as intended, and yet his plaque kept progressing. Because controlling blood pressure is not the same as activating reverse cholesterol transport. The medication was doing its job. The exit door was never opened. His ABCA1 was not being activated. The cholesterol inside those foam cells had nowhere to go. That changes today. Has your doctor ever discussed cholesterol efflux capacity with you, or have every conversation about your lipid panel ended at the HDL number? Drop it in the comments. Now, I need to be very precise here because the category of food isn't enough. The specific quality within that category is what determines whether the biology actually happens. Not olive oil, not light olive oil, not the bottle that says made with olive oil. High-phenolic extra virgin olive oil, and I'm going to explain exactly why those words matter. In 2017, a research team published findings in Frontiers in Pharmacology that I consider one of the most underreported studies in nutritional cardiology. Healthy volunteers consumed extra virgin olive oil daily for 12 weeks. The researchers weren't just measuring cholesterol numbers, they were measuring the actual biological mechanisms, the exit door. The results: cholesterol efflux capacity, the ABCA1-mediated ability of foam cells to eject cholesterol back to HDL, increased by 44% compared to the control group. The messenger RNA responsible for producing ABCA1, essentially the instruction signal telling cells to build more exit doors, increased by 16%. A related transporter called ABCG1, which works alongside ABCA1 in the same efflux process, increased by 35%. Let me translate what that means in plain language. Extra virgin olive oil didn't just reduce LDL oxidation, which is what most people focus on when they think about olive oil and heart health. It activated the transporter that runs the exit out of the foam cell. Those are two completely different biological events, and most heart-healthy dietary advice only addresses the first one. Think of it this way. You're trying to fix a flooding basement. Most advice focuses on stopping the water from coming in, fixing the leak, waterproofing the walls. That matters. But if the drain at the bottom of the basement is blocked, the water that's already in there has nowhere to go. The basement stays flooded even after you fix the leak. ABCA1 activation is opening the drain. And for most people following standard heart-healthy advice, that drain has never been opened. Now, what makes this happen? What's actually in the olive oil that produces this effect? Two compounds, allicin and erythritol. These are polyphenols, plant compounds found in significant concentrations only in high-quality, minimally processed extra virgin olive oil. Here's the critical detail. Standard olive oil extracted with heat degrades these polyphenols. The refining process that makes olive oil lighter, milder, and more shelf-stable also removes the compounds responsible for the ABCA1 effect. The middle shelf bottle, the one that's been sitting in a clear glass container under fluorescent supermarket lighting, may have too little allicin to produce any measurable biological response. Quality isn't a preference here, it's a mechanism. A 2013 randomized crossover trial confirmed this in pre-hypertensive patients. 30 milliliters of high-phenolic extra virgin olive oil with a polyphenol content of 961 milligrams per kilogram produced significantly increased ABCA1 expression in peripheral blood leukocytes. These are the white blood cells that eventually become macrophages in the arterial wall. The olive oil wasn't just passing through the digestive system and showing up in the bloodstream. It was producing measurable changes in gene expression, the actual instructions inside the cells that determine what proteins get built and in what quantities. That's not just a nutritional effect. It's a documented biological response to specific compounds in a food. Then there's Predimed. Published in the New England Journal of Medicine in 2013, 7,447 participants.
5 years, all at elevated cardiovascular risk. 3 groups: Mediterranean diet supplemented with extra virgin olive oil, Mediterranean diet supplemented with nuts, and a control group following standard low-fat dietary advice. The extra virgin olive oil group showed a 30% reduction in cardiovascular events. The low-fat group had the worst outcomes, not second worst, worst. Now, I want to explain exactly why, because this is the part that should change how you think about the low-fat advice most people in this audience have received at some point. A low-fat diet reduces dietary fat intake broadly. When you reduce fat across the board, you also reduce HDL, because HDL production is partially dependent on dietary fat. When HDL levels fall, the reservoir that accepts cholesterol from foam cells via ABCA1 becomes smaller. Follow the logic. You're reducing LDL inputs, which is good, fewer LDL particles entering the arterial wall. But simultaneously, you're shrinking the HDL reservoir, which means even the ABCA1 exit doors that are open have fewer trucks waiting outside to carry the cholesterol away. You're fighting on one front and quietly retreating on another, and the net result, as Predimed documented in nearly 7,500 real people over 5 years, was worse than the group eating more fat from high-quality olive oil. This isn't an argument against reducing LDL. It's an argument for understanding that cardiovascular biology has multiple moving parts, and optimizing one while ignoring the others is not a complete strategy. 3 months ago, I was reviewing the original Predimed dose curves, specifically looking at whether the 30 milliliter daily threshold was meaningful or just an artifact of the study protocol. The evidence suggests the effect is genuinely dose-dependent. Below 20 milliliters per day, roughly 1.5 tablespoons, the ABCA1 activation benefit diminishes substantially. 3 to 4 tablespoons of high-phenolic extra virgin olive oil per day is the range where two separate mechanisms are simultaneously operating: ABCA1 activation from the oleasin and erythrodiol, and nitric oxide production from the hydroxytylosol and oleocanthal, which we'll cover in detail in mechanism 3. Same ingredient, same dose, two completely different biological pathways, both active at the same time. That's not a coincidence. That's why dose and quality matter. A drizzle of standard olive oil over a salad isn't activating either pathway at a meaningful level. Has your doctor ever discussed cholesterol efflux capacity with you? Or has every conversation about your lipid panel ended at the HDL number? Drop your answer in the comments. I read every one. Mechanism 2 is different in a fundamental way from everything we just covered. Mechanism 1 was about the foam cell, cholesterol that got trapped inside the arterial wall and needs a biological exit to come back out. That's a removal problem. Mechanism 2 is about something else entirely, something that happens in a different layer of the arterial wall, driven by a completely different biological process and requiring a completely different compound to address it. Mechanism 2 is about calcium, and the reason this matters, the reason I'm spending significant time on it, is that most people who are actively managing their cardiovascular health have never been told that calcium deposits in arteries are not inevitable, that there's a protein your body already produces specifically designed to prevent arterial calcification, and that whether that protein works or sits completely inactive depends almost entirely on whether you have adequate levels of one specific nutrient that the Western diet is almost universally deficient in. Let me give you an analogy before we get into the mechanism, because once you have the right mental picture, the science becomes straightforward. Imagine your arterial wall employs a security guard. His one job, intercept calcium crystals before they can embed themselves into the arterial tissue. He's trained, he's positioned correctly, he's ready to work. But here's the problem. In order to do his job, he needs a specific piece of equipment, a kind of molecular catching mitt that allows him to grab the calcium crystals and neutralize them before they cause damage. Without that equipment, he stands there, present, willing, completely unable to function. That security guard is a protein called matrix Gla Protein, or MGP. It's produced by the smooth muscle cells in your arterial wall. Its entire purpose in life is to bind to calcium crystals before they can incorporate into arterial tissue. The equipment he needs, the catching mitt, is vitamin K2.
Without adequate K2, MGP is produced in what's called its uncarboxylated form. Uncarboxylated MGP cannot bind calcium. It's the security guard standing at his post with no equipment, watching calcium crystals walk right past him and embed themselves into the arterial wall. With adequate K2, MGP gets carboxylated, activated. Now it can do its job. It intercepts the calcium. The crystals don't deposit. The arterial wall stays flexible. This single mechanism, MGP activation via K2, is the difference between arteries that stay elastic and arteries that gradually harden over decades. Now let's look at what the research actually shows, because the numbers here are remarkable and remarkably underreported. The Rotterdam study, 4,807 adults over the age of 55, followed for 8 to 11 years. Researchers tracked dietary K2 intake against cardiovascular outcomes, not blood markers, not surrogate measurements, actual outcomes. The results from the highest K2 intake group: 50% reduction in arterial calcification, 50% reduction in cardiovascular risk, 25% reduction in all-cause mortality. A 50% reduction in cardiovascular risk in a population study of nearly 5,000 adults, tracking real events over nearly a decade.
And here is the detail most people miss when they hear this study cited. The protective effect was specific to K2, not K1, not vitamin K as a general category, K2 specifically. That distinction matters enormously, and it's where a lot of well-intentioned people are getting incomplete information. Most people who are health conscious eat leafy greens, spinach, kale, broccoli, and they feel confident they're getting their vitamin K. They are, but they're getting K1, which is abundant in green vegetables and plays an important role in blood clotting. K1 and K2 are not the same molecule. They have different structures, different transport mechanisms in the body, and critically, different biological targets. K1 goes primarily to the liver, where it supports clotting factor production. Its effect on arterial calcification is minimal. K2, specifically the form called MK7, found in fermented foods, distributes to soft tissues throughout the body, including arterial walls. It's the form that activates MGP. It's the security guard that reaches MGP. You can eat leafy greens every day, genuinely excellent dietary behavior, and still have MGP that is predominantly inactive because you're getting the wrong form of K for this specific job. The Western diet is almost universally deficient in K2, not K1, K2. And that deficiency is silently allowing calcium to deposit in arterial walls in millions of people who believe they're eating well. The Prospect EPIC cohort, 16,000 women aged 49 to 70. Researchers tracked dietary K2 intake against cardiovascular disease incidence over years of follow-up. Finding: every additional 10 micrograms per day of K2 produced a 9% reduction in cardiovascular risk. 10 micrograms. That's a tiny amount. The fact that even incremental increases in K2 at that scale produced measurable risk reduction tells you something important about how deficient most Western populations are at baseline. Then there's the randomized controlled trial published in Thrombosis and Hemostasis in 2015. 180 micrograms of K2 as MK7 daily for 3 years. At the end of 3 years, the K2 group showed decreased arterial stiffness. The control group showed increased arterial stiffness over the same period. Not plateau, not maintenance. The control group's arteries became measurably more stiff over 3 years, while the K2 group's arteries became measurably more elastic. That's 2 groups of people aging differently over 3 years, and the difference was 1 compound at 1 dose taken daily. If you watched Your Stiff Arteries Are Starving Your Brain After 60, you remember Thomas, calcium score of 981 at baseline. After 18 months on a protocol that included daily K2 supplementation, his calcium score had dropped to 841. That's a regression of 140 points on a calcium score, a metric that in most people following standard cardiovascular care either stays flat or continues to climb. At the time I presented Thomas's case, I showed you the outcome. Today, I'm giving you the mechanism. K2 was activating his MGP. Carboxylated MGP was intercepting calcium crystals before they could deposit, and over 18 months, the calcification process was not just slowing, it was reversing. The security guard finally had his equipment. Thomas's case is presented here as an illustrative example of what the research supports mechanistically.
Calcium score regression is not a guaranteed or typical outcome. Individual results vary significantly based on baseline health, compliance, and other factors. Now let me be very specific about practical sources, because K2 is one of those nutrients where the form and the dose both matter significantly. Option A, natto, a Japanese fermented soybean product and the single most concentrated natural source of K2-MK7 on the planet. 50 grams of natto provides approximately 200 micrograms of MK7, slightly above the therapeutic dose used in the clinical trial.
The flavor and texture are an acquired taste. Some people grow to love it, many don't. But if you're open to it, 50 grams daily puts you at the top of the therapeutic range from a single whole food source. Option B, aged Gouda, 5 years or older. 3 ounces provides approximately 60 micrograms of MK7. Genuinely useful as a contribution to total daily K2 intake, though unlikely to reach the full 180 microgram therapeutic target on its own. Option C, supplemental MK7 at 180 micrograms daily, the most practical option for most people in a Western dietary context. One important detail: K2 is fat-soluble. It requires dietary fat to be absorbed properly. Consuming K2 with this meal, which includes 3 to 4 tablespoons of high-phenolic extra virgin olive oil, puts it in optimal absorption conditions. The same fat-activating mechanism 1 is also the carriers that allows mechanism 2 to be absorbed and utilized, a built-in synergy. For anyone on anticoagulant medication, including warfarin, Eliquis, Xarelto, Pradaxa, or any other blood thinner, have a specific conversation with your prescribing physician before adding K2. This is not a reason to avoid it. It's a reason to have an informed conversation first. Of vitamin K1 and K2, do you know which form your diet is actually providing and at what level? And has anyone ever explained the difference to you in a clinical setting? Drop it in the comments. Before I get to mechanisms 3 and 4, of the first 2 mechanisms, ABCA1 and MGP activation, which one, if either, was already in your approach? Drop it in the comments. We've covered 2 mechanisms so far. Mechanism 1 opens the exit door, pulling cholesterol out of foam cells and back into the bloodstream via ABCA1. Mechanism 2 activates the security guard, preventing calcium from embedding itself into the arterial wall via MGP and K2. Both of those mechanisms operate inside the arterial wall, working on a process that's already in motion. Mechanisms 3 and 4 work differently. Mechanism 3 addresses the environment the arterial wall lives in, the quality of the endothelium, the flexibility of the vessel itself, the biological conditions that determine whether the cascade accelerates or slows. Mechanism 4 goes even further upstream. It intervenes before the cascade begins, at the very first step, before LDL even has a chance to oxidize and trigger the immune response that starts everything. Together, they complete the picture, and together they explain why the protocol works as a system rather than a collection of individual ingredients. Most people have never thought about nitric oxide in the context of their cardiovascular health. It doesn't show up on a standard lipid panel. Your doctor almost certainly hasn't mentioned it, and yet it may be one of the most important molecules in your entire arterial system. Here's the simplest way to understand what nitric oxide does. Think of your arteries as living tubes, not rigid pipes, but dynamic, responsive tissue that expands and contracts with every heartbeat. The inner lining of those tubes, the endothelium, is constantly receiving signals and adjusting the diameter of the vessel in response. Nitric oxide is the primary signaling molecule that tells your arteries to relax and expand. When nitric oxide is abundant, your arteries dilate, blood flows freely, and the mechanical stress on the arterial wall is reduced. When nitric oxide is depleted, the opposite happens. Arteries become stiffer, blood pressure rises. The endothelium becomes dysfunctional, less able to respond to signals, more permeable to LDL penetration, more vulnerable to the cascade we described earlier. Nitric oxide depletion isn't just a symptom of arterial disease. In many cases, it's a driver of it. Now here's what makes mechanism 3 genuinely remarkable and what most discussions of nitric oxide completely miss. There are 2 entirely separate biological pathways that produce nitric oxide in your arterial wall. They use different raw materials, they operate at different points in the biology, and they have different points of failure. The protocol activates both of them simultaneously.
Pathway 1. The dietary nitrate route.
You eat arugula, which contains high concentrations of inorganic nitrate. As you chew, bacteria naturally present on the surface of your tongue convert that nitrate into nitrite. You swallow. In the acidic environment of your stomach, some of that nitrite is converted directly into nitric oxide. The rest enters the bloodstream, where endothelial enzymes complete the conversion. The result? Vasodilation, improved arterial elasticity, reduced pulse wave velocity, meaning your heart doesn't have to work as hard to push blood through the system. But here's something most people don't know, and it has a practical implication that affects millions of people every morning without them realizing it. The bacteria that initiate this entire pathway live in your mouth, specifically on the surface of your tongue and in the grooves between your teeth. Antiseptic mouthwash, the kind that kills 99.9% of oral bacteria, sterilizes your oral microbiome, including exactly the bacteria you need to convert nitrate to nitrite. Studies on chlorhexidine-based mouthwash find it reduces salivary nitrate-reducing activity by over 90% for several hours after use. You eat the arugula, the nitrate arrives in your mouth, but the bacteria that should convert it are gone. The pathway stalls at the very first step. This is why the recommendation is simple. Brush and floss. Avoid antiseptic mouthwash. If your dentist has prescribed an antiseptic rinse for a specific condition, periodontitis, post-surgical care, follow their guidance. But for most people without that specific indication, routine antiseptic rinsing is removing the bacteria that make Pathway 1 work. Pathway 2, the enzymatic route. This pathway operates completely independently of dietary nitrate. Different raw materials, different trigger, different point of activation. In the endothelial cells lining your arterial wall, there is an enzyme called eNOS, endothelial nitric oxide synthase. Its job, convert an amino acid called arginine into nitric oxide directly inside the endothelial cell without requiring any dietary nitrate as a starting material. What activates eNOS? Two compounds found in high-phenolic extra virgin olive oil, hydroxytyrosol and oleocanthal. This is the same ingredient we introduced in Mechanism 1, but activating a completely different biological pathway. In Mechanism 1, oleosine and erythritol were opening the ABCA1 exit door for cholesterol. Here, hydroxytyrosol and oleocanthal are activating the enzymatic production of nitric oxide directly in endothelial cells. Same bottle of olive oil, two separate biological mechanisms, both requiring the same quality threshold and the same daily dose. When both pathways are active simultaneously, nitric oxide production in the arterial wall is additive, not redundant, where activating both gives you the same result as activating one. Additive, where the combined effect is greater than either pathway alone. A 2024 Umbrella review published in the Journal of Functional Foods examined 113 studies across 2,013 participants, examining dietary nitrate and vascular outcomes. The findings: dietary nitrate reduced pulse wave velocity, reduced augmentation index, and increased flow-mediated dilation, three separate markers of arterial health, all improving simultaneously. In the protocol we're building, high-phenolic extra virgin olive oil at 3 to 4 tablespoons per day and raw arugula at 2 to 3 cups are consumed in the same meal. Both pathways active. The synergy is documented. Now here's the part that connects directly to what we covered in Mechanism 1 and makes it even more significant. A low-fat diet impairs both nitric oxide pathways simultaneously. Eliminating high-phenolic extra virgin olive oil removes hydroxytyrosol and oleocanthal. Pathway 2 loses its activator. and the higher carbohydrate intake that typically replaces dietary fat raises triglycerides, which impairs endothelial function and degrades pathway 1 as well. Both routes deteriorate together. While the person following the diet believes they're doing everything right, the Predimed results have been documenting this since 2013, and there are still millions of people being told to cut fat broadly, without being told what they're removing along with it. That's not a failure of intention, it's a failure of translation. Everything we've covered so far, ABCA1, MGP, nitric oxide, operates downstream of a trigger. That trigger is LDL oxidation. Remember the cascade from earlier. LDL enters the arterial wall. It oxidizes. The immune system misidentifies it as a foreign invader. The macrophage engulfs it. The foam cell forms. The foam cell dies.
The debris accumulates into plaque. Every step in that cascade follows from the first one, LDL oxidation. Mechanism 4 acts before that step. It doesn't clean up the damage, it doesn't open exits or activate security guards. It goes to the very beginning of the sequence and makes LDL significantly harder to oxidize in the first place. If LDL doesn't oxidize, the immune system doesn't recognize it as an invader. The macrophage doesn't engulf it, the foam cell never forms, the cascade never starts. The compound that does this comes from pomegranate, and it works through a mechanism that is more precise and more elegant than most people realize. Imagine every LDL particle in your bloodstream as a cargo ship carrying cholesterol. The ship has a hull, a protective outer coating. As long as the hull is intact, the ship moves through the bloodstream without triggering any alarm. The immune system sees it, recognizes it, leaves it alone. Now imagine that hull slowly corroding, oxidizing as the LDL particle sits trapped in the arterial wall. A corroded hull looks different. The immune system no longer recognizes it. It looks like wreckage, like something dangerous that needs to be dealt with. And that's when the macrophage moves in. The polyphenols in pomegranate, specifically a class of compounds called punicalagins, act like a protective coating on that hull. They bind directly to the outer surface of the LDL particle, attaching to a protein called APO100, the structural shell that surrounds every LDL particle. With punicalagins bound to that surface, the LDL particle becomes significantly more resistant to oxidative modification. The hull stays intact longer. The immune system keeps recognizing it as familiar. The macrophage stands down. The cascade doesn't start. There's a second layer to how punicalagins work, and this one connects mechanism 4 directly back to mechanism 1. Punicalagins also upregulate an enzyme called PON1, paraoxinase 1. Think of PON1 as a patrol system riding along with your HDL. HDL is already doing the job of accepting cholesterol from foam cells via ABCA1, that's mechanism 1, but with an active PON1 patrol on board, your HDL is simultaneously neutralizing oxidized lipids in the bloodstream, reducing the oxidative burden on the arterial wall, and making the entire reverse cholesterol transport process more effective. Higher PON1 means more capable HDL. More capable HDL means greater cholesterol efflux capacity. Greater cholesterol efflux capacity means mechanism 1, ABCA1, works better. Mechanism 4 potentiates mechanism 1. The 4 mechanisms aren't just parallel interventions. They're connected. They reinforce each other. Clinical evidence. Researchers studied patients with carotid artery stenosis, narrowing of the arteries supplying the brain, over 1 year of daily pomegranate consumption. At the end of 12 months, in the pomegranate group, carotid intima media thickness, the standard ultrasound measurement used as a proxy for plaque burden, had decreased. In the control group, it had continued to increase.
A 2025 randomized controlled trial published in Nutrients, conducted in adults aged 55 to 70, confirmed improved endothelial function and increased nitric oxide availability from pomegranate extract. Mechanism 4 connecting to mechanism 3, the system working as a system. Now, I need to be very precise about form because getting this wrong can actively work against you. Industrial pomegranate juice delivers punicalagins. That part is correct. But it also delivers a significant payload of free fructose, sugar that has been separated from its natural fiber matrix during processing. That free fructose load activates your liver to produce more fat, raises triglycerides, and drives the production of small, dense LDL particles, a particularly dangerous form of LDL that penetrates the endothelium more easily and oxidizes more readily. In other words, industrial pomegranate juice gives you the shield while simultaneously sending more vulnerable ships through the arterial wall. The correct form is pomegranate arils, the whole seeds, eaten as they come from the fruit. 1 cup of pomegranate arils provides approximately 300 milligrams of punicalagins, the dose used in the carotid stenosis regression study, delivered within an intact fiber matrix that dramatically slows fructose absorption. Same molecule, completely different metabolic outcome, because the matrix the molecule arrives in changes everything about how your body processes it.
Before we move to the complete protocol, of the 4 mechanisms we've covered, which one was missing from your current approach? ABCA1, MGP, nitric oxide, or LDL oxidation protection? Drop it in the comments. I read every one. Let me give you the complete picture before I give you the protocol. We've covered a lot of ground in this video. Foam cells, calcium crystals, nitric oxide pathways, oxidized LDL, and if any of it felt dense at moments, if there were points where you had to slow down and rewind, that's not a sign that this is too complicated for you. That's a sign that nobody has ever taken the time to explain it to you properly. Because this information exists. It's been published, it's been peer-reviewed, it's been sitting in academic journals for years. It just never got translated. So before we go to the protocol, here is the complete picture in plain language. Mechanism 1, ABCA1 activation via high-phenolic extra virgin olive oil, opens the exit door that pulls cholesterol out of foam cells and into HDL for elimination. Most people's diets never open it. Mechanism 2, MGP activation via K2-MK7. Activates the protein that intercepts calcium crystals before they embed in the arterial wall. The security guard was already there. K2 was the equipment he needed. Mechanism 3, dual pathway nitric oxide via arugula and extra virgin olive oil simultaneously. Keeps the arterial wall elastic, the endothelium functional, and the environment resistant to LDL penetration. 2 separate pathways, both active at the same time. Mechanism 4, LDL oxidation prevention via pomegranate arils. Stops the cascade before it starts by protecting LDL from oxidizing and boosts HDL's ability to run mechanism 1 at the same time. 4 mechanisms, 4 different points in the same disease process, each documented, each requiring a different compound, each failing to compensate when the others are missing. Here is exactly what the research supports: every ingredient, every dose, every reason. Ingredient 1, raw arugula, 2 to 3 cups. Mechanism activated, pathway 1 nitric oxide, vasodilation, reduced arterial stiffness, improved endothelial function. Why raw? Cooking degrades dietary nitrate. To get the nitric oxide benefit, the arugula needs to be consumed raw. Why arugula specifically? Arugula is among the highest nitrate leafy greens available in standard Western supermarkets. Pathway 1, the dietary nitrate route. You eat arugula, which contains high concentrations of inorganic nitrate. As you chew, bacteria naturally present on the surface of your tongue convert that nitrate into nitrite. You swallow. In the acidic environment of your stomach,
Some of that nitrite is converted directly into nitric oxide. The rest enters the bloodstream, where endothelial enzymes complete the conversion. The result? Vasodilation, improved arterial elasticity, reduced pulse wave velocity, meaning your heart doesn't have to work as hard to push blood through the system. But here's something most people don't know, and it has a practical implication that affects millions of people every morning without them realizing it. The bacteria that initiate this entire pathway live in your mouth, specifically on the surface of your tongue and in the grooves between your teeth. Antiseptic mouthwash, the kind that kills 99.9% of oral bacteria, sterilizes your oral microbiome, including exactly the bacteria you need to convert nitrate to nitrite. Studies on chlorhexidine-based mouthwash find it reduces salivary nitrate-reducing activity by over 90% for several hours after use. You eat the arugula, the nitrate arrives in your mouth, but the bacteria that should convert it are gone. The pathway stalls at the very first step. This is why the recommendation is simple. Brush and floss. Avoid antiseptic mouthwash. If your dentist has prescribed an antiseptic rinse for a specific condition, periodontitis, post-surgical care, follow their guidance. But for most people without that specific indication, routine antiseptic rinsing is removing the bacteria that make Pathway 1 work. Pathway 2, the enzymatic route. This pathway operates completely independently of dietary nitrate. Different raw materials, different trigger, different point of activation. In the endothelial cells lining your arterial wall, there is an enzyme called eNOS, endothelial nitric oxide synthase. Its job, convert an amino acid called arginine into nitric oxide directly inside the endothelial cell without requiring any dietary nitrate as a starting material. What activates eNOS? Two compounds found in high-phenolic extra virgin olive oil, hydroxytyrosol and oleocanthal. This is the same ingredient we introduced in Mechanism 1, but activating a completely different biological pathway.
Practical note: fresh pomegranate arils are available pre-packaged in most major supermarkets. Frozen arils retain polyphenol content well and are available year-round. Ingredient 4. Vitamin K2 MK7, 180 micrograms. Mechanism activated? Mechanism 2. Carboxylation of matrix Gla protein, interception of calcium crystals, prevention of arterial calcification, and maintenance of arterial elasticity. 3 practical options. Option A. Natto, 50 grams, approximately 200 micrograms of MK7, the most concentrated natural source. Specific texture and flavor, an acquired taste that not everyone enjoys, but worth trying. Option B. Aged Gouda, 5 years or older, 3 ounces, approximately 60 micrograms of MK7, a useful contribution to daily K2 intake. Pairs naturally with the arugula in this meal. Option C. Supplemental MK7, 180 micrograms with this meal, the most practical option for most people. Taking with the first bite of a fat-containing meal, the olive oil in this protocol provides optimal absorption conditions. Critical note for anticoagulant users: if you are taking warfarin or any other vitamin K-dependent blood thinner, have a specific conversation with your prescribing physician before adding K2. This is not a reason to avoid K2. It's a reason to have an informed conversation first. Putting it all together. A large bowl of raw arugula, 2 to 3 cups as the base. 1 cup of pomegranate arrows distributed through the salad or on the side. 3 to 4 tablespoons of high-phenolic extra virgin olive oil as the dressing, applied generously, not as a drizzle. 50 grams of natto alongside, or 3 ounces of aged Gouda,
or 1 MK7 supplement taken with the first bite. 4 mechanisms, 1 meal, 10 to 15 minutes to prepare, every day. This is not a recipe, this is a protocol. 4 simultaneous biological interventions, each targeting a documented step in the arterial disease process, each supported by peer-reviewed clinical evidence, consumed together in a form and dose that reflects what the studies actually used. If you've been following this series, these ingredients should feel familiar because each one connects to something we've covered before. If you watched "Your pressure is controlled, your plaque is ignored," you now understand exactly why arrows and not juice. The fructose cascade that drives small dense LDL is the upstream problem that mechanism 4 is designed to address, and industrial juice would undermine that protection from the inside. If you watched "Your stiff arteries are starving your brain after 60, you now have the other side of Thomas's story. His medication managed the endothelial pressure. This protocol activates the biology the medication was never designed to touch. They are not alternatives, they are complementary. And this protocol extends beyond the heart. The same arugula that reduces pulse wave velocity in your aorta activates nitric oxide in the cerebral vasculature. The same extra virgin olive oil that activates ABCA1 in your coronary artery wall activates nitric oxide in the cerebral vasculature. The pipe and the garden are one system. This protocol is the intervention for both. 3 actions, starting this week. Action 1. Build the meal this week, not after more research, not after you find the perfect olive oil, this week. The arugula is in every supermarket. The pomegranate taros are available fresh or frozen. The olive oil decision takes 15 minutes of label reading. The K2 supplement is 1 click away. $10 to $15 per day. 10 minutes to prepare. The logistics are genuinely not the obstacle. Action 2. Verify your olive oil today. Go to your kitchen right now and find the bottle you're currently using. Does it state polyphenol content in milligrams per kilogram? Does it say extra virgin? Is it stored in dark glass, away from heat and direct light? You may have the category right, you may not have the quality right. Those are 2 completely different things with 2 completely different biological outcomes. If the bottle doesn't pass those 3 questions, replace it. Action 3. Bring this to your next medical appointment. Here is the exact language to use. I've been reading about ABCA1 activation and cholesterol efflux capacity, matrix Gla Protein activation via Pay2-MK7, dual pathway nitric oxide production, and pomegranate punicalagins in the context of LDL oxidation prevention. Given my calcium score and current medications, does this 4-component dietary protocol make sense alongside my existing treatment plan? And is there a way to track progress through a cholesterol efflux capacity assay or serial calcium scores? That question signals that you've done serious research. It invites a genuine clinical conversation, and it immediately tells you whether your physician is current on this literature, because the terms are specific enough that a physician familiar with this research will respond very differently than one who isn't. You deserve that conversation. These questions have earned a real answer. The recap. 1. Arterial plaque builds through a cascade with 4 separate biological intervention points. Most dietary advice activates one of them. 2. The 4 mechanisms: ABCA1 activation via high-phenolic extra virgin olive oil, MGP activation via K2-MK7, dual pathway nitric oxide via raw arugula and extra virgin olive oil simultaneously, LDL oxidation prevention via pomegranate arrows upstream of the entire foam cell cascade. 3. These 4 mechanisms are simultaneously activatable in one meal at doses that correspond to the studies producing the documented results. 4. The mechanisms reinforce each other. The system is integrated, and the integration is not accidental. You weren't missing effort. You were missing 3 of the 4 mechanisms your body needs. I want to be honest about something before we finish. I read this research because someone I loved followed incomplete advice for years and paid for that incompleteness with his health. My father did everything he was told. He was diligent, consistent, compliant in a way that most patients never manage to be. And he was working with an incomplete map. The 4 exits I've shown you today, ABCA1, MGP, nitric oxide, punicalagins, those exits existed when he was walking his 3 miles every morning. The research was being published. The mechanisms were being documented. Nobody translated it for him. I cannot go back and change that, but I can make sure that the people watching this video today, people who are asking the right questions, who are willing to read and learn and push for better answers, have access to the translation. That's what this channel is. If you're walking away from this video differently than you walked in, if something clicked, if a gap got filled, if you're thinking about your arterial health in a way you weren't an hour ago, drop "informed" in the comments. I read every single one. If this is the kind of work you want to keep seeing, the evidence base, the mechanisms, the translation, the subscribe button is there. I don't post every day. When I post, it's this. And there is someone in your life right now, someone who is walking their 3 miles and taking their medication and following their doctor's advice and still progressing, who needs to see this video before their next cardiology appointment. You know who that person is. Send this to them. One final note before you go. I read the research and I translate it. I am not your physician. Nothing in this video is a substitute for medical supervision or a replacement for your current treatment plan. Every intervention I've described should be considered alongside your existing care, not instead of it. The protocol and the medication work on different parts of the same biology. They are complementary by design. If you are on warfarin, Eliquis, Xarelto, Pradaxa, or any other blood thinner, have a specific conversation with your prescribing physician about K2 before adding it. If you have an existing cardiac diagnosis, bring this protocol to your cardiologist using the language I gave you in Action 3. This works best as a collaboration, an informed patient and a current physician working together, both looking at the same evidence, asking the same questions. That collaboration starts with you walking into the appointment informed. That's what this video was for. Of the 3 actions, verify your olive oil, build the meal this week, bring the question to your next appointment, which one are you doing first? Drop it in the comments.